Okay, so let's get started. So we spent quite a bit of time with graph theory in the first part of this course, and today I want to move beyond that. So we're going to talk about more central topics in additive combinatorics, starting with the Fourier analytic proof of Roth's theorem. We discussed Roth's theorem and we gave a proof earlier in the course using Semiratis's graph regularity lemma as well as the triangle removal lemma. Today I want to show you a different approach to proving Roth's theorem that goes through Fourier analysis. So this is a very important proof and it's one of the main tools in additive combinatorics. Let me remind you what Roth's theorem says. So Roth proved in 1953 that if we write R sub 3 of interval n to be the maximum size of a 3AP free subset, of 1 through n, then Roth showed that R3 of n is little o of n. Okay, so in other words, if you have a positive density subset of the integers, then it must contain a three-term arithmetic progression. Okay, so what I said is equivalent to this statement here. So previously we gave a proof using regularity. Actually, the regularity approach of Semiratis was only found in the 70s. So Roth's original proof was through Fourier analysis. And we'll see that tomorrow. Today we'll see a toy version of this proof. Well, it's not really a toy version. It is the same ideas, but in a slightly easier setting that has fewer technicalities. But before showing you that, let me just discuss a bit of history around Roth's theorem. We will show next time. So next lecture, we'll show the bound. Also by regularity, we get some bound which is little o of n, but because of the use of regularity lemma, it's a pretty poor dependence. We got something like n over log star n. Next lecture, and basically Roth's original proof gives you a bound which is n over log n. Right? So it's a much more reasonable bound. The current best upper bound known has the form essentially n over log n raised to 1 plus little 1. So roughly n over log n. We do not know or even have great guesses on what the answer should be. So the best lower bound, and this is a construction that we saw earlier in the course due to Behrend, is of the form n over e to the c root log n. It seems it may be very difficult to improve this upper bound without some genuine new ideas. On the other hand, there is some evidence that the lower bound might be closer to the truth, in that there are variants of the Roth problem for which we know that the lower bound is basically the truth. What I want to do today is look at a variant of this problem in what's called a finite field model. And that basically just means we're going to be looking at Roth's theorem not in the integers, but in some finite field vector space, specifically f3 to the n. So we're going to define R sub 3 of this f3 to the n to be the maximum size of 3AP free subset of this finite field vector space. So the finite field model is really useful. We're going to see this again later in the course as well. Many of the ideas, techniques that work for the real problem, so to speak, many of those techniques also work in the finite field model, but they're technically simpler to execute. So this is often, you see, can view it as a sandbox, a playing ground for testing out many of the ideas. And once you have those ideas, then you can see if you can bring them to the integer setting. Right, so this is a very successful program, and we'll see one aspect of what happens when we do this. For this specific problem of Roth's theorem in f3 to the n, there are some nice interpretations of what this problem means. Right, so here's a pretty easy fact that so in f3 to the n, for 3 elements x, y, z, the following interpretations of what it means to be a 3AP are equivalent. So x, y, z form a 3AP. Okay. So 3AP means the y is x plus d, z is x plus 2d. Equivalently, they satisfy this equation, x minus 2y plus z equals to 0. Okay, in f3, minus 2 is plus 1. So it's the same as this even nicer looking equation, x plus y plus z equals to 0. It also turns out to be the same as saying that x, y, z, they lie on a line. So they are a line. Right, so the line has 3 points in f3. And if you look at the coordinate for every I, the ith coordinate of x, y, z are all distinct or all equal. Okay, so easy to check. All these things are equivalent to each other. And the last one has a nice interpretation in terms of a game that many of you know, a set. So in the game set, you have a bunch of cards. There are some number of properties, n properties, like color, the number of symbols, the shape. And you want to form a set being 3 cards such that every property, they're all same or all different. Okay, so that's exactly this model over here. All right, so what can we say about this problem? What's the size of the maximum subset of f3 to the n without 3AP? If you look at the proof that we did earlier in this course, the one using triangle removal lemma, you see the proof works verbatim, right? Previously, we worked over Z mod n. Now you work over a different group. Same proof. So triangle removal lemma, it tells you that this R3 is always little o of the size of the space. But we would like to do better. Right? So this gives you something like log star. It's not very good dependence. So we would like to do better. So what we will show today, okay, so this theorem is attributed to Meshulam. So in this case, the order of history is somewhat reversed. So we'll see the finite field toy model, but it historically actually came afterwards. But you'll see that the Fourier analytic proof that we'll see today, it's basically the same proof in the 2 settings. So f is R3. We will prove a bound which is like that. Okay, so much better than what you get from the regularity method. In terms of, okay, so let me tell you a bit more about the history of this problem in terms of what we know in terms of upper bounds and lower bounds. Okay, so let me say more about F3. So what's the best that you might hope for? So the best lower bound is, okay, so due to a del, and it's some construction, some very specific construction, which gives you a bound that's something like 2.21 to the n. And the upper bound is 3 to the n, right? On the 3 minus little 1 to the n. So for a long time, it was open whether the answer should be basically roughly like 3 to the n or some constant less than 3 to the n. And improvements on the upper bound were very slow, and there were some very difficult works that nudged that bound below just a little bit. And then a few years ago, there was this incredible breakthrough where in this paper that was just a couple pages long, they managed to significantly improve the upper bound to basically 2.76 to the n. So this was an incredible breakthrough that happened just a few years ago, and we'll talk about this proof in a couple of lectures. It turns out this proof, which uses what's now called the polynomial method, so not Fourier analytic, but a different method, unfortunately does not seem to generalize to the original Roth theorem. In fact, you shouldn't expect it to generalize in a straightforward way, because up there, you know that you do not have a power saving, whereas here you have a power saving, right? So the exponent goes down. Okay, so this is roughly the history of this theorem. Any questions? So yeah, so I can tell you this is known as a crude left pack. Okay, so I'll say more about it in a couple lectures, but this for F3 is due to Ellenberg and Heischweid. Okay, so I'll tell you more about it in a couple lectures. What I want to focus on today is the Fourier analytic nature of the proof that gives you this bound up there, 3 to the n over n. And it might seem like a completely different topic compared to what we've been doing so far in the course, which is more about graph theory. But I want you to think about what are the relationships between what we'll say today and what we've seen so far. And there are lots of connections, right? So even though the proof might superficially look quite different, many of these ideas about quasi-randomness versus structure will come up. And I want to present the proof in a way that highlights the similarities between what we did previously and this Fourier analytic proof. So let's talk about the strategy. In the proof of the Semirati graph regularity lemma, we had this strategy that we call the energy increment strategy. So you want to find a good partition, you start doing partitioning, and you keep track of this thing called the energy. Must go up at every step, cannot go up forever, so has a bounded number of steps. The strategy for Roth's theorem is also an important strategy. It's a variant of energy increment, but now density increment. So we start with a set, a subset of F3 to the n, and we would like to understand something about its structure versus pseudo-randomness in a way that is similar to when we discussed the similar issue for graphs. And in particular, there will be this dichotomy that if A is, in some sense, pseudo-random. Okay, so earlier we saw what it means for a graph to be pseudo-random. So now what does it mean for a subset of F3 to the n to be pseudo-random? So we'll address that today. If A is pseudo-random, so the short answer is that it is Fourier uniform. In other words, all Fourier coefficients small. Okay, so that's what pseudo-random will refer to. So then there is a counting lemma. And the counting lemma will in particular imply that A has lots of 3APs. Okay, so then you find your 3AP. If this is not the case, then, okay, so what's the opposite of Fourier uniform is that A now has some large Fourier coefficient. And what we'll do is to use this Fourier coefficient to extract some codimension 1 affine subspace it's also called a hyperplane, where the density of A goes up significantly if you restrict to that hyperplane. Right. And you can repeat this process. Now restrict to this hyperplane and ask yourself the same question. Is A, when restricted to this hyperplane, pseudorandom, in which case we find A piece? Or is A restricted to this hyperplane, does it have a large Fourier coefficient, in which case we restrict further? And each time you iterate, you obtain a density increment. And the density increment cannot go on forever because your total density is at most 1. So the number of steps must be bounded. Okay, so that's the strategy. So it should remind you somewhat of the energy increment strategy from Similarity's regularity lemma, although there are some fundamental differences. We're not doing partitionings. Any questions about the strategy? Okay. I want to tell you about Fourier analysis. So probably all of you have seen some version of Fourier analysis, maybe in your calculus class with Fourier series and whatnot. And okay, so you play with formulas and solve some differential equations. So I want to give you, more than just a bunch of ways about handling Fourier coefficients, a way to think about Fourier analysis. Right? So think of this as a crash course about Fourier analysis from the perspective of combinatorics. And Fourier analysis, I think, is much easier if you work in a finite group, in a finite abelian group, which is what we're doing here. Many of the technicalities go away. So we'll be looking specifically at Fourier analysis in f3 to the m, although the 3 can be any prime, right? So it's really the same. So the main actors in Fourier analysis are the Fourier characters. The Fourier characters are denoted gamma sub r, and they are characters on the group, meaning that they are maps, which so they turn out happen to be homomorphisms to the multiplicative group under so C under multiplication, and they're indexed by R, which are also elements of F3 to the n. Okay, so I'm going to be fairly concrete here. There are ways to do this more abstractly, but I'll be fairly concrete. So it's defined by gamma sub r, evaluated on x, equals to omega raised to r dot product x, where here omega is a third root of unity, and the dot is a dot product. So so that's the definition of the Fourier transform. Oh, sorry, that's the definition of the Fourier characters. And once you have the Fourier characters, you can have this Fourier transform, which is defined as follows. If you start with a function, let's say a complex valued function on your space, then I define the Fourier transform to be another function like that, defined by the following formula. Okay, so that's the formula for the Fourier transform. It is basically the inner product between f and the Fourier character. And so let me make the comment here. I think this is actually a pretty important comment about the normalization. Now, when you first learn Fourier transforms, usually in the reals, there are always these questions about what number to put in the exponent. Is it 2 pi? Is it root 2 pi? Is it some other thing? And somehow one answer is better than the others. And the same thing is true here in groups. So we'll stick with the following convention, and I want all of you to stick with this convention, otherwise we'll confuse ourselves to no end. Is that for a finite group, actually, let me start a new board. So the convention is that in a finite group, the Fourier transform is defined, and more generally, anything you do in the physical space, we always use the averaging measure. Don't sum, always average in the physical space. And in the frequency space, always use sums. Okay, use the counting measure. Keep this in mind. Any of these questions about normalization, if you stick with this convention, things will become much easier. So there won't be any of these questions about when you take the inverse Fourier transform, do I put an extra factor in front or not, if you stick with this correct convention. So with that convention in mind, what a Fourier transform really is an inner product between f and a Fourier character. Okay. There are some important properties of the Fourier transform. So let me go through a few of the key properties that we will need. The first one is pretty easy. What is the meaning of the 0th Fourier coefficient? You plug it in, and you see that it is just the average of f. Okay? Right, so the 0th coefficient is the average of f. The second fact goes under one of two names, and they're often used interchangeably, Plancharel or Parseval. And it says that if you look at the inner product in the physical space, then this inner product is preserved if you take the Fourier transform. But now, of course, you're in the frequency space, so you should sum instead of doing the inner product. Okay, so this identity can be proved in a fairly straightforward way by plugging in what the definition is for the Fourier transform. Now, this is a straightforward computation I'm not going to do on the board, but I highly encourage you to actually do it at home. Not just to do it once to make sure you understand how it goes. But there's also a more conceptual way to understand this identity. And that's because, okay, and this is also important to understand what the Fourier transform is. It's not just some magical formula somebody wrote down. Like this is a very natural operation. It's because the characters, the set of characters, is an orthonormal basis. So the Fourier characters form an orthonormal basis. As a result, what the Fourier transform is a unitary change of basis. You can check, it's very straightforward to check that the Fourier characters indeed form an orthonormal basis because, well, you can evaluate the inner product between two Fourier characters. So remember, in the physical space, we're always doing averaging. And so now, okay, so I'll just write down first what I mean by the inner product. So that's the inner product. And by the definition of the Fourier character, you have that. So think about what this expectation is. Right? Unless R equals to S, in which case this expectation is 1. Okay, unless that is the case, you always have some coordinate of x in the exponent. So as you average over all possibilities, they average out to 0. Okay. So this calculation shows you that the Fourier characters form an orthonormal basis. And the basic fact you know from linear algebra is that if you do a change of basis, if you do a unitary change of basis, then inner product is preserved. Right? It's like a rotation. It's the same, so you're not changing the inner product. So the inner product is preserved under this change of basis. And that's why Planck-Rowe is true. Another important thing is what's known as the Fourier inversion formula. The Fourier transform tells you how to go from a function to the Fourier transform. Well, now, if you are given the Fourier transform, how do you go back? There's a formula which tells you that you can go back by the following formula there. Okay? So that's the Fourier inversion formula. It allows you to do this inversion. And again, it's one of these formulas where I encourage you to try it out yourself by plugging in the formula and expanding, and it's pretty easy to check. It's much easier in the finite field setting, by the way. So if you use the usual Fourier transform on the real line, there are some technicalities even to prove the Fourier inversion. But in finite groups, it's almost trivial. You expand, and then you will see. Right? So it's very easy to prove. But you can also see this Fourier inversion formula more conceptually because you are in a unitary change of basis. So to go back, well, think about what it means in linear algebra to revert a unitary transformation. You simply multiply the coefficients with the coordinates. Orthogonal, orthonormal change of basis. Finally, Fourier transform behaves well under convolution. Right, so by convolution, we define the convolution of two functions, f and g, using the following formula. Okay. And so then the claim is that the Fourier transform behaves very well under convolution. It's basically multiplicative under convolution. Right? Okay, so what this means is if I put in, so it's pointwise true everywhere. Okay. Again, very easy proof because I just evaluate the left-hand side, see what, plug in the formula for the Fourier transform, and I find it's that. And now I plug in the formula for convolution. Okay. And okay, so now you can do a change of variables, and okay, so then it's not hard to see, you eventually end up at the right-hand side. Okay, so these are some of the properties. So there are important properties of the Fourier transform. So this is something that, whenever you learn about the Fourier transform, you always see these few properties. And so we'll use them. But we'll also need another property that is specific to the analysis of three-term arithmetic progressions. So what does Fourier transform have to do with 3APs? So we want to use it to prove Roth's theorem, so we better have some tool that allows us to analyze the number of 3APs. And here's the key identity relating Fourier with 3APs. And it's that if you have three functions then the following quantity, which relates the number of 3APs, okay, so this function basically counts the number of 3APs if your f, g, and h are indicator functions of a set. I want to express this formula in terms of the Fourier transforms of these functions. The formula turns out to be fairly simple, that it is simply that. Okay, so it's a single sum over the r's of f hat of r, g hat of minus 2r, and h hat of r. You might wonder why I put a minus 2 here, because minus 2 is r, and it looks certainly much nicer with just r in there. And that is true. This formula, as written, is true for over any group. And our proof will show it. So it's not really about F3 at all, but any group. Let me prove this for you in a couple of different ways. So the first proof is basically a straightforward, no thinking involved proof. As in, we apply these formula for using either Fourier inversion or the inverse Fourier transform, and plug it in and expand and check. Okay, so it's worth doing at least this once. So let's do this together at least once. But this is something that is a fairly straightforward computation. The left-hand side can be expanded using Fourier inversion. So R1 f hat R1 omega to the minus R1 dot x, and sum over R2 g hat R2 omega to the minus R2 dot x plus y. And then finally, sum over R3, h hat of R3 omega to the minus R3 dot x plus 2y. Okay, so I'm using Fourier inversion, replace f, g, and h by their Fourier transforms. Oh, sorry, there should be no minus. Okay, so now we exchange sums and expectations, do a switch in the order of summation. So R1, R2, R3, and F hat of R1, G hat of R2, H hat of R3, and you have this expectation over x and y, and omega of x dot R1 plus R2 plus R3. In fact, I can even write the x and y separately. Y omega to the y dot R2 plus 2R3. Okay, so just rearranging. And now you see that as you take expectation over x, this expectation is equal to 1 if R1 plus R2 plus R3 is equal to 0, and 0 otherwise. And likewise, the third expectation is either 1 or 0, depending on the sums of R2 and R3. So the only terms that remain after you take out these zeros are cases where both these two equations are satisfied. And then you see that the only remaining terms are basically the ones given in the sum on the right-hand side. Okay, so that's the proof. Pretty straightforward. You plug in Fourier inversion. I want to show you a different proof that hopefully will be more familiar and more conceptual, that doesn't involve carrying through this calculation, even though this is not at all a hard calculation. But first, let me rewrite the formula up there. So in F3, so it will be convenient, and so the formula is actually slightly easier to interpret in F3. In F3, the identity says that if you look at the quantity on so let me give you a second proof that works just in F3, but you can modify it to work in other groups. But in F3, it's particularly nice. The left-hand side, you see, the left-hand side, I can rewrite it as the following form, where I sum over, or I take expectation over all triples, x, y, z, that sum to 0. Because a 3AP is the same as 3 elements, 3 points in the vector space summing to 0. But now you see that this quantity is the same as the convolution evaluated at 0. So if you extend the definition of convolution to more than 2 functions. But now we apply Fourier inversion. And we find that so by Fourier inversion, you have that. But now, by the identity that relates the Fourier transform and inversion, you have that. Okay. And that's the proof, right? Because minus 2r is the same as r. Okay. So it's shorter because we're using some properties here about convolution and so about the convolution. That formula up there is of course related to counting 3 APs, because if F, G, and H are all indicators of some set, then the left-hand side is the same as basically the number of triples of elements in A whose sum is equal to 0. And the right-hand side is the sum of the third power of the Fourier coefficients. And this formula should look somewhat familiar because we also used this kind of formulas back when we discussed spectral graph theory. And remember, the third moment of the eigenvalues is the trace of the third power, which counts closed walks in a Cayley graph. So this is actually the same formula. So in the case, if A is symmetric, let's say, then this is the same as the formula that counts closed walks of length 3 in a Cayley graph. The point of this comment is just to tell you that Fourier transform is somehow it's not this brand new concept that we've never seen before. It is intimately tied to many of the things that we have seen earlier in this course, but in disguise. Right? So it is related to the spectral graph theory that we discussed at length earlier in this course. Okay? Now that we have the Fourier transform, I want to develop some machinery to prove Roth's theorem following the strategy up there. Okay, so let's take a quick break, and then when we come back, we'll prove Roth's theorem. Any questions so far?
So for this one, you said, is it like we only used the fact that it's f3 to the n like at the end of the proof, like in that last step?
Okay, so question is, where do we use that word in f3 to the n? This formula here holds in every finite abelian group if you use the correct definition of Fourier transform with the averaging normalization. Right, so in the other formula where you replace -2 by 1, that requires f3. But you can follow the proof and come up with a similar formula for every equation. Yeah, so there's a general principle here, which I'll discuss more at length in a bit, that for patterns that are governed by a single equation, in this case, 3 APs, x minus 2y plus z equal to 0, patterns that can be governed by a single equation can be controlled by a Fourier transform. Okay. All right, so let's begin our proof, the Fourier analytic proof of Roth's theorem in f3 to the n.
So at the end, you said there was like a connection with counting blocks in a graph. Does this mean that like the Fourier transform of like the indicator of A, those are exactly the eigenvalues of the Cayley graph, or is it like a little bit?
Okay, so you're asking about the final step where we were talking about. So I mentioned that there's this connection between counting walks in graphs and spectral graph theory. So you can check that if you have a subset A of an abelian group, then the Fourier transforms of A are exactly the eigenvalues of the Cayley graph.
So I guess like, have we done anything so far that could have been done in a spectral way yet? Or I guess like, where is like the Fourier analysis better than just the spectral approach?
Okay, question, where is the Fourier analysis better than the spectral approach? So let's see the proof first, and then you'll see. Yeah. So there's no graphs anymore. Right? So we're going to work inside f3 to the n. But just like the proof of regularity and counting, we're going to have a counting lemma. Okay, so all of these are analytic, and at this point, they should be very familiar to you. They may come in a different form, they may be dressed in different clothing, but it's still a counting lemma. So let's see. Okay, the counting lemma in this case says that if you are in the setting of a f3 to the n, and I'm going to throughout write the density of A as alpha, then let me define this lambda 3 of A to be the function which basically counts 3 APs in A, but with the averaging normalization. Okay, so we saw this earlier. So the counting lemma says that this normalized number of 3 APs in A, so including trivial 3 APs, right? So this is a nice analytic expression, differs from what you might guess based on density alone. This difference should be small if all the non-zero Fourier coefficients of A are small. So in the strategy, I said that so the counting lemma tells you if A is Fourier uniform, then it is pseudo-random. And this is where it comes in. If A has all small Fourier coefficients, then you have a counting lemma, which tells you that the counts of A should not be so different from the guess based on density. Right, so the proof is very short. It's based on the identity that we saw earlier. The 3 AP count of A by the identity earlier is simply the third power of the Fourier transforms. Okay, and again, all of these calculations should be reminiscent because we've done these kind of calculations in some form or another earlier in this course. So we're going to separate out the main term and subsequent terms. Right, so the main term is the one corresponding to r equals to 0. So that's the density. And all the other terms I'm going to lump together into this sum. So we now know that the difference we're trying to bound is upper bounded by the third moment of the absolute values of the Fourier transform. And I want to upper bound this quantity here, assuming that all of these Fourier coefficients are small. We've also done this kind of calculations before. Okay, so where have we seen this before? We saw this calculation earlier in the class with a 3 replaced by a 4. Okay, so in counting 4 cycles in the proof of equivalence of quasi-randomness, we said that if all the eigenvalues other than the top one are small, then you can count 4 cycles. It's the same proof. And remember, in that proof, there was an important trick where you do not uniformly bound each term by the max, because then you lose. You lose by an extra factor of n that you don't want. So you only take out one factor. So you take out one factor, and you keep the rest in there. In fact, I can be more generous and even throw the r equal to 0 term back in. And now, by Plancherel, Parseval, this here is equal to the expectation of a, the indicator function of a squared, right? So you take this, you go back to physical space, and that's simply the density. Okay? So then that proves the theorem. Okay, so the moral of the counting lemma is the same as the one that we've seen before when we discussed graphs. If you're in pseudo-random, then you have good counting. And here, pseudo-random means having small Fourier coefficients, uniformly small Fourier coefficients. So now let's begin the proof of Roth's theorem. Okay. The Roth theorem proof will have 3 steps. The first step, we will observe that if you're in a 3AP3 set, then there exists a large Fourier coefficient. Throughout, I'm going to use uppercase N to denote the size of the ambient group. And specifically, we will prove the following. Okay, and also throughout, A is a subset of F3 to the N, and with density alpha. So I'll keep this convention throughout this proof. We will show that if A is 3AP3, and N is at least 2 to the alpha to the minus 2, so N is at least somewhat large, then there exists a non-zero R such that the R Fourier coefficient is at least alpha squared over 2. If you're 3AP3, then provided that you're working in a large enough ambient space, you always have some large Fourier coefficient. Right, so the proof is essentially, this claim is essentially a corollary of counting lemma. By the counting lemma, and using the fact that in a 3AP3 set, what is the quantity lambda 3 of A? Up there, you only have the trivial 3APs present. So this quantity lambda must then be the size of A divided by n squared, or alpha over n, which are precisely counting the trivial 3APs. Okay, so by the counting lemma, then we have that the upper bound on the right-hand side, which is now write alpha max over non-zero R's, is at least alpha cubed minus the lambda 3 term, which should be alpha over n. So provided that n is large enough, big N is large enough, then the trivial 3APs should not contribute very much. So I can lower bound the right-hand side by, let's say, alpha cubed over 2. So then you deduce the conclusion. Again, I want you to think about how this proof is related to similarities graph regularity lemma. The analogy will break down at some point, but we've seen this step before as well. From lack of 3APs, you extract some useful information. And from this, we'll extract some structure. And the structure here, and this is where the proof now diverges from that of regularity. Having a large Fourier coefficient will now imply a density increment on a hyperplane. Specifically, if you have, okay, so keeping the same convention as before, if the Fourier coefficient of A at R is at least delta for some non-zero R, then A has density at least alpha plus delta over 2 when restricted to a hyperplane. Restricted to so if you have a large Fourier coefficient, then I can pass down to a smaller part of the space where the density of A goes up significantly. To see why this is true, let's go back to the definition of the Fourier coefficient, the Fourier transform. So recall that the Fourier transform is given by the following formula, where I'm looking at this expectation over points in f3 to the n together with the indicator of A multiplied by this Fourier character. And you see that this function here, it is constant on cosets of the hyperplane defined by the orthogonal complement of R. Right? So the value of this dot product is constant on the three hyperplanes. So I can rewrite this expectation simply as 1/3 of alpha naught plus alpha 1 omega plus alpha 2 omega squared, where alpha naught, alpha 1, alpha 2 are the densities of A on the three cosets of R perp. Okay, so group this expectation into these three hyperplanes. So now you see that if this guy is large, then you should expect that alpha naught, alpha 1, and alpha 2 are not all too close to each other. Certainly if they were all equal to each other, you should get 0, but you should not expect them to be too close to each other. In particular, we would want to say that one of them goes up, is much bigger than alpha. So one of these then must be much bigger than alpha. That's an elementary inequality. This is something that I'm sure I give you 5 minutes you can figure out. But let me show you a small trick to show this. And the reason for this trick is because in next lecture, when we look at Roth's theorem over the integers, we'll need this extra trick. And the trick here is this. We now know that because of the hypothesis, 3 delta is the lower bound to the absolute value of alpha naught plus alpha 1 omega plus alpha 2 omega squared. And okay, so note here that the average of the 3 alphas is equal to the original alpha by definitions of density. So this inner sum I can rewrite like that. Okay, so the sum of the 3 roots of unity add up to 0. And now I apply triangle inequality. To extract the terms. Okay, so now you should already deduce that one of the alpha i's has to be significantly larger than alpha. It has to be significantly different, but there are only 3 terms. One of them has to be significantly larger. But let me do this one extra trick, which we'll need next time, which is that let me add an extra term like that, which sums out to 0. But now you see that each summand is always non-negative. Right? So there exists some j such that delta lower bounds the jth summand. And if you look at what that means, then, okay, so alpha lower bounds the jth summand. So in particular, this sum here should be non-negative. Okay, so you have that. Good. Okay, so we obtain a density increment on this hyperplane. And finally, I want to iterate this density increment. So I want to iterate this density increment So summary so far is that we have, so if A is 3AP free with density alpha and at least 2 to the alpha to the minus 2, then A has density at least alpha plus alpha squared over 4 on some hyperplane. Right, so you combine step 1 and step 2, we obtain this conclusion. Well, I can now repeat this operation. Right, so I can repeat by restricting A to this hyperplane. Right? If A is originally 3AP free, I restrict it to hyperplane, it's still 3AP free. So I can keep going. I can keep going provided that my space is still large enough, right? Because I still need this lower bound on n. Okay, so don't forget this one here. So I can keep going as long as n is, so I'm using n sub j to denote what happens after the jth step. I can keep going as long as this is still satisfied. But of course, you cannot keep on going forever because the density is bounded. Right? So density cannot exceed 1. So these two will give you a bound on the total dimension. So let's work this out. So let alpha I denote the density after step I in this iteration. And we see from over here that you start with density alpha, and each step you go up by an increment, which is basically what, okay, so you go up by some increment. And you want to know, if you start with alpha, how many steps at most can you take before you blow out 1? Okay, so can you give me some bound? So what's the maximum? So at most, how many steps? So we know that the density cannot exceed 1. Okay, so see that you have at most 4 over alpha squared steps. Okay, so because density is at most 1. And if you plug this in, you get something which is not quite what I stated. So it turns out that if you plug this in, you find that alpha is, you find that the size of A is at most 3 to the n over square root n. Okay, so let me do a little bit better. Right? So then simply seeing that this term here is at least alpha squared over 4. And the point is that when you increment faster and faster. Right? So I can use that to give a better bound on the number of steps. Right? And here's the way to see it. Okay, so we can do better. So starting at alpha, and then now ask how many steps do you need to take before it doubles? Well, it goes up by alpha squared over 4. So it doubles after at most 4 over alpha steps. And at which point this alpha, new alpha, becomes at least the original, twice the original alpha. But now you keep going. How many times does it take to double again? 2 over alpha, because the alpha became twice as much. So doubles again after at most 2 over alpha steps. Right? And then you keep going. The next iteration is 1 over alpha. So in total, right, so you see that we must stop after at most 8 over alpha steps. So the number of times it doubles actually decreases by at least half each time. All right. So now we know that we see that so you keep on going, so you must stop after at most 8 over alpha steps. What is the final density when you have to stop? Okay, so when are you forced to stop? You are forced to stop if you run out of space. Okay, so you're forced to stop when you run out of space. So if the process terminates after m steps, okay, so we're at density alpha m. So then the final space, subspace, has size less than 2 to the alpha m to the raised to minus 2, which is, okay, so now I use this bound alpha. So the initial n is upper bounded by what? So how many steps did you take? You took at most 8 over alpha steps. Each of those steps, you pass down to codimension 1. You lose a dimension for each step. And the final subspace has at least this, has at most that many, that much space. So the final dimension is this basically log 1 over alpha. Okay, so put them together, we see that the size of the space originally is at most 1 over alpha. Yeah.
Should this be a lowercase m?
Thank you. Yeah. there should be a lowercase n, so the dimension. Okay. Right. And okay, so then that's the conclusion. That the density alpha is big O of 1 over n. Okay, that proves the main theorem for today. So Roth's theorem over f3 to the n. Okay, so we went through this Fourier analytic proof. Next lecture, we will see the same proof again, but done in the integers for interval. And there's some difficulties that we don't see over here. Because in the finite field space, in the finite field model, there's this very nice idea of looking at subspaces. Right? So looking at hyperplanes. Each Fourier coefficient gets you down to 1 dimension less. But when you're working in the integers, there are no subspaces you can use. Okay, so we'll be looking at ways to get around the lack of subspaces. And this is why I said in the beginning that the finite field model is often a very good playground for, for additive combinatorics type techniques, especially Fourier analytic techniques. Because in the additive, in all of these techniques, they just come out to be much cleaner if you're working in a finite field setting. You have nice subspaces, you have Fourier transform in a very clean way. The Fourier transform always takes, in this case, one of 3 values. Right? Everything's very clean, everything's very simple, and you get to see the idea here, you get to see this density increment argument. But once you understand those ideas, and you're willing to do more, more work, then oftentimes you can bring those ideas to other settings, to other abelian groups, to the integers, for instance. But with more work there's some extra ingredients that you need to use. I mentioned that there was a bound. Okay, so initially, so next time we'll see that. Next time we'll see what happens over the integers. Any questions? Yes. Okay, great. So questions, why the process must stop after at most 8 over alpha steps. So you know that the density doubles after this many steps, doubles again after that many steps. So eventually, if it keeps on doubling, it cannot keep on doubling forever. Right? So this process cannot keep on doubling forever, so it must stop. So cannot double more than log base 2 of 1 over alpha times. Okay, at that point you have to stop. So how many steps have you taken? Well, you sum this geometric series. So this sum, and the next thing is, you sum this geometric series, and that geometric series sums to 8 over alpha. Okay. Great, so let's finish here. So next time we'll see Roth's proof of Roth's theorem.